So, now up to now what we have discussed is normal LDA or LSDA functional. We came to know what is meta GGA, what is GGA, hybrid. Now, we go to the next round of accuracy, and before going into that, this picture given here which is taken from this reference is called a Jacob's ladder. Now, if you search in the Wikipedia, you will see that Jacob's ladder is something has a different origin. It has its mention in the biblical literature in the book of Genesis, where the patriarch Jacob in his dream sees a ladder to the heaven. So, similar stories exist in our literature also. We know of the Ravan wanted to build a golden ladder to the heaven, but in the case of DFT, this is generally mentioned to describe the systematic way of improving DFT functionals from in the terms of getting more accuracy at the expense of more computational cost. The philosophy is actually same as wave function based methods, where you want to get systematic accuracy and at least this Jacob's ladder gives you a recipe to get you a systematic way of accuracy, but remember the exchange correlation functionals are fitted with respect to arbitrary parameters. So, this becomes like a semi empirical method at the end. So, it is not always true that when you go up the ladder you always get more accurate answer, but the qualitative trend generally the more you go up into the ladder you get more accuracy. So, the lowest rung in this ladder is LDA, next one is the second rung is GGA, third rung is meta GGA, fourth rung is the hybrid function, and the fifth rung where you come with the double hybrid. So, as I go up the ladder my accuracy increases, of course, my simplicity decreases and my functions become more and more complicated. So, the highest rung in that ladder is called double hybrids. So, what you do is that in the case of hybrid, what we were doing is that to calculate the exchange correlation functional or even GGA meta GGA, we are using only summing over up to the occupied orbital for both for the Coulomb term as well as the kinetic energy term. What you do in the case of double hybrid is that not only occupied, but you also use the information available with the virtual orbital. So, a general double hybrid DFT functional will look like this one. So, it will have the DFT exchange plus Hartree-Fock exchange, DFT correlation plus the correlation which is obtained from the MP2 method. So, that means now whatever you are trying to guess from the DFT correlation, it is actually very small because most of the correlation is actually coming through the MP2. Now, the MP2 term is calculated as similar as the normal traditional MP2 molar pressure perturbation theory, which uses Fock operators as its 0th order Hamiltonian, but here in this case the MP2 term is calculated using DFT orbitals and orbital energies. Now, you may say that okay, why only use DFT? I can use some more accurate methods, like I can use maybe MP3 or couple cluster for the thing. So, one problem is that if I want to do really MP3 or couple cluster, then why I am even bothered using DFT. And the other problem what has been observed is that just adding more and more a higher correlation method does not necessarily improve the quality of double hybrid results. So, that something is problematic, and that is what many wave function theorists generally scoff at the double hybrid, that you are now cooking up something mixture where you take a wave function correlation and then add it with the DFT functional exchange correlation functional. But generally the RPA kind of method gives you a more theoretical work to go into more accurate functionals using the RPA kind of a framework. Now, advantage, so double hybrid results are generally very accurate. It's sometimes can go to up to CCSD parenthesis T level accuracy or approach that. And second advantage is that it allows you to have a qualitative description of the dispersion. We have just discussed that in case of normal DFT functional, even for a hybrid, the accurate description of dispersion is a problem, and we have seen the example of argon dimer where you can see when we do not have this dispersion corrections, the actually does not lead to any binding. Whereas, in the case of double hybrid, it actually gives you some kind of a binding. So, that is one advantage. However, the computation cost is like MP2. not only computation cost is like MP2, its basis set convergence behavior is also like MP2. So, it converges very slowly because I have an MP2 part. So, triple zeta numbers are often not good enough. You either need to go at least quadruple zeta, better if you can go to pentaple zeta or extrapolate to the complete basis set limit. So, gives you more accuracy, computationally higher cost. Why you should use it? Because it still may be slightly cheaper for doing single point calculation than using a CCSD parenthesis, and the results are generally much more reliable. Now, among the DFT functionals available in the ORCA, there is B2 PLIP, B2 GP PLIP, the DSD functionals. So, my personal favorite is B2 PLIP because this is one of the first one, but you may try your own. So, now the homework problem for you will be recalculate the proton affinity value what we have already done, and remember you have to still do it with M062X and MP2. We have not done it, that was an homework problem. So, that you also should do using B2 PLIP, and the dispersion correction problem what you have done for argon dimer, that you also should try using B2 PLIP. So, this will be your homework problem. Before I close, I want to discuss something is the effect of DFT grids on your calculation. This is a topic generally most of the cases people avoid. Now, remember we have discussed that the exchange correlation functional has been calculated numerically on the top of grids, and there are various grids settings available at various steps. So, ORCA used like combined grid settings where one grid keyword actually set all the other grid settings. So, they are called def grid 1, def grid 2, def grid 3. In principle, it can be possible to modify all these 3 grids by using appropriate keywords, but that is not at all recommended. In case of ORCA, the default grid is def grid 2, which is always is most of the cases actually gives very good answer. If you want to use a more tighter grid, you can use def grid 3, and if you want to use a slightly smaller grids, then you can use def grid 1. Remember, larger grid setting I use, so I go from 1 to 3, my energies become much more accurate, but my computation cost is increasing. So, if you are using a previous version of the ORCA, remember there is a major overhaul of the DFT grids, and the present grid setting is much more accurate than what was available previously, and these grid settings are present in any other DFT software you are using. So, we will test how the grid settings actually going to affect your results, and we are going to only in this lecture we are only going to check the energy, but remember this DFT grid settings can also affect your geometries, maybe frequencies. The default grids is generally good for almost every purposes, but there may be some cases where you want to check the def grid 3 results to make sure that you are getting correct trends. Now, what we will do here, we will take 2 example. One is Si5H12 and second one is Al4P4, and we are going to calculate the energies in this 3 grid setting. I will take the def grid 3, which is the tightest of all the grid, as my reference, and with respect to that I will see how much energy changes when I use the default grid of grid 2 or I use the default or the def grid 1. So, and why I have chosen this particular system, because you see the example of Si5H12. So, this contains silicon. So, it is actually on the 3rd period, and this one the hydrogen is from the 1st period in the table, whereas in the case of aluminum actually belong to the 3rd period, and this one actually belong to the 3rd period. So, this one contains more heavier element than this present one, and we will see how the grid settings actually affect them. We are still not into the optimization, and I spent some time today morning to optimize the ALP4 geometry, making the Si5H12 is easy using Avogadro, you can try it. So, but I have given the geometry here, so you can just use them. So, let us first try with the Si5H12. So, this is the geometry here. So, we will just copy it copy it, I go to Notepad, create an input file, so the method we were going to use test is B3lib MADEF to SVP. So, it is B3lib MADEF to SVP. I will use Rij cos x, of course, and this is an XYZ file, XYZ format. Charge and multiplicity is 0 and 1, and because my reference is default grid 3, so let me write default grid 3, def grid 3. So, let me save it. So, I write it as SI5 H12 G3 because it is default grid 3. This calculation may take some time. So, let me open the file. By the time it will run, I can show you some part of it. So, it says that integral accuracy is 9.959, angular grade is 6, and angular, that is basically correspond to the radial grades. Actually, the angular grade correspond to 6, and the angular grade pruning method is takes at 4. So, remember this sitting 4.959 and 6, and we will see how the energies in the other cases looks like. This calculation, as we discussed, can take some time. Actually, one of the problem in this case is that you cannot really see the output files how when it is getting updated. So, by that time let me save this one as plot. And let me close it, and let me start a new Excel file. where I write the molecule name, grid name, so first let me write the molecule name here, H12, and this is the energy, and this is change in energy, and this is the time required for calculation to be finished. Okay, my calculation is done. Let me run the second calculation. So this is INP. So now let us go to the default grid. For the default grid, grid 2, you do not need to do actually anything. You actually save it as G2. Dot INP. You could have written as default grid 2 also. That should not have mattered. So by the time it runs, let me go to the G3 output file. We have already discussed what the grid settings were. So the two things I will pick up from here is, first of all, is the energy. And the time required was 179.109 second. Here if you open the output file, you will see that your integral accuracy from 4.38, if I go it here, this was 4.959. From there in the default grid, it has become 4.388, and my angular grid, what was 6, now has become 4 in the default grid. So, time taken is less, now 121. For def grid 2. And the energy is this one. Now try default grid 1. So, I write it as def grid 1 and save it as and run the calculation again for the grid setting 1. Similarly, I can make the input file for AL4P4. So, I can go to the pad and I can take any of the input file. I can change the geometry, put the AL4P4 geometry here. This looks little strange, so we have to edit it. Def grid 3, save as L4P4.inp. Oh, to write it G3 because it's the grid 3 I am using. Let me run the Orca job for L is small, L4 P4 G3 dot inp. It's very rhythmic. 4 P4 G3 dot out. some problem in the name. Let's see. What is the name I have saved with? I forgot to give the dot. Let's rename dot .inp. Again it has needs to be renamed because this has saved it as a text file. So, I will go there. Save as. L4 G P4 G3. Okay, let us make now the input file for the L4P4. So, I can use this one, I can copy the content, looks little bit weird, so I have to do some editing. Yep. So, now let me save it. It's all files. I will call it L4 P4 G3 Rhythmic. I save it. Now, let's Orca L4 P4 G3 L4 P4 G3 dot out. By the time it runs, let me have the grid 1 output file, and if you see the grid settings here for the grid 1, you see the integral accuracy is 4.159. In G2 it was 4.38, and the angular grid was 3. In the both of the cases is actually angular grid is actually 3, but the integral accuracy has reduced a lot. Now let us put the energy here for the SiG1. Now time taken is now see the change in the value. The value is actually generally very small. So, let us convert it to kilojoule per mole. What was the conversion factor? It was here 2625.49. So, let me copy it. So, it is very less in case of kilojoule. So, if I write it C2 minus C4, then it comes to 0.1 kilojoule. So, 0.1 kilojoule may not be a very big number, because this cannot be achieved in any of the theoretical method, even does not with couple cluster. Also, you see the timing, like this one, the tightest grid depth grid 3 actually takes almost 3 minutes, the default grid take 2 minutes, and the depth grid 1 is slightly smaller. And my AL4 job is still running, because it is an heavier element. So, let me prepare the input file for G3 and G1. So, this is G2. And now for G1. So, now all our calculations are done. Let us open the output file one by one. So, this is the G3 output file. This is the total energy. Okay, let me start from here, maybe. Energy, change in energy, time required. These are my grid names, and this is AL4P4. And time, this took actually some time. almost 7 minutes. Now let us go to def grid 2. This took only 74 seconds. So now you see for how much the grids can affect. Now let us see the grid 1. Slightly smaller time. I could just use this expression. I missed the minus sign here. Is 0.13. Is 0.71. So, it is almost reaching 1 kilojoule per mole. So, two things to notice from here. First of all, how the grid settings actually affects the timing. So, if you use the grid 3, actually the computation times increases significantly. So, your default grid actually hits a sweet spot between the timing and the computational accuracy. Grid 1's results are slightly more inaccurate. The other interesting thing to notice is that if your molecules contains heavier elements, so your grid settings are much more important, because loose grid setting leads to much more error than what you have seen for more lighter element. And this is not even transition metals. So, for transition metals, the grid settings can lead you to slightly larger errors. If your molecule is quite big, then the geometries can be problematic, and especially if you are dealing with cases where the electron density is away from the nuclear framework. For example, if you are dealing with anions, you should be very careful about the default grid setting. So, this is what we wanted to discuss about the DFT. I hope in this week's class it is give you some idea about the theories of DFT. This week particularly went into too much of the theory. We discuss about why DFT is important and what is the main benefit. Benefit is dimension reduction, and then we discuss that what is the problem of writing that energy in terms of density. The biggest problem is that you cannot actually write the kinetic energy as only in terms of density. You have to write it in terms of one particular reduced density matrix. We came into Kohn-Sham theory, we understood of different approximation, LDA, G, then when it only depends upon the local density, then you can correct for the gradient, it leads to GGA. You can even include higher order terms, it leads to meta GGA. We have learned about adiabatic connection theorem, what is hybrid, especially we discussed the functional form of B3-lip, we went into range separated functional. We discussed how to do dispersion corrections, and dispersion corrections are important. It is almost negligible cost. So, you should always use D3 or D4 corrections with it. We talked about double hybrid and we discussed what is the advantage, and also we discussed about grid settings. Now, with this one we will go into practical applications. So, next week we will discuss about potential energy surface and how to optimize geometry, find out transition state and how to study chemical reaction. So, see you next week. Thank you.